Hi friends, today we'll discuss about regular and non-regular languages. The language A star B star is regular, whereas the language A raised to n B raised to n, where n is greater than or equal to 0, is not regular. The language W belongs to AB whole star, where every A is immediately followed by a B, is regular, whereas every A has a matching B somewhere and no B matches more than one A is not regular. Then the question is, given a new language L, how can we know whether it is regular? How many regular languages are there? The theorem states there are countably infinite number of regular languages. As a proof, we can enumerate all the legal DFSMs with input alphabet summation. Every regular language is accepted by at least one of them. So, there cannot be more regular languages than there are DFSMs. But the number of regular languages is infinite because it includes the following infinite set of languages consisting of 1A, 2A, 3As, 4As, 5As, 6As and so on. Thus, there are at most a countably infinite number of regular languages. There are many languages which are regular, but how can we know which ones? For that, the theorem states every finite language is regular. As a proof, if L is the empty set, then it is defined by a regular expression null, and so is regular. If it is any finite language composed of strings s1, s2, so on up to sn for some positive integer n, then it is defined by the regular expression s1 union s2 union s3 so on up to union sn. So, it too is regular. Let's see some examples. A finite language L is equals to W belongs to 0 to 9 whole star, where W is the social security number of a living US resident. L is regular because it is finite. Let's see one more. The intersection of two infinite languages. Let L is equals to L1 intersection L2, where L1 is A raised to n, B raised to n, where n is greater than or equal to 0. L2 is B raised to n, A raised to n, where n is greater than or equal to 0. We already know that neither L1 nor L2 is regular, but the intersection L is equals to L1 intersection L2 is equals to epsilon, which is finite, hence regular. The regular expressions are most useful when the elements of L match one or more patterns. Finite state machines are most useful when the elements of L share some simple structural properties. Other techniques like hash tables are better suited for handling finite languages whose elements are chosen by our word rather than by rule. 4 techniques to show that the language, finite or infinite, is regular. First, write a regular expression for the language. Second, design a finite state machine for the language. Third, show that the number of equivalents of the language is finite. And fourth, write a regular grammar for the language. Some of the closure properties of regular languages are: the regular languages are closed under union, concatenation, clean star, complement, intersection, difference, reverse, and letter substitution. If we wish to show that some language L is regular, and we can show that L can be constructed from other regular languages using these operations, then L must also be regular. So let us see all these properties one by one. The regular languages are closed under union, concatenation, and clean star. By the same constructions that we used in the proof of Klint's theorem, we can prove it. For this proof, you can refer regular expressions video. Regular languages are closed under complement. Proof: if L1 is regular, then there exists a DFSM M1 is equals to K summation delta SA that accepts it. The DFSM M2 is equals to K summation delta S K minus A, namely M1 with accepting and non-accepting states swapped accepts complement of L of M1 because it rejects all the strings that M1 accepts and accepts all the strings that M1 rejects. Given an arbitrary NDFSM M1 is equals to K1 summation delta 1 S1 A1, construct an equivalent DFSM M2 is equals to K2 summation delta 2 S2 A2 such that L of M2 is equals to complement of L of M1 using NDFSM to DFSM algorithm. First step is from M1 construct an equivalent deterministic finite state machine M dash is equals to Km dash summation delta M dash Sm dash Am dash. If M1 is already deterministic, then M dash is equal to M1. Second step, M dash must be stated completely. So, if needed, add dead states and all transitions to it. Begin building M2 by setting it equal to M dash. Swap accepting and non-accepting states. So, M2 is equals to Km dash summation delta M dash Sm dash Km dash minus Am dash. For example, let L be a language over summation 0, 1 containing the strings ending with 0, 1, and this is the DFSM obtained for this particular language. On interchanging the non-accepting to accepting state, non-accepting to accepting state, accepting to non-accepting state, we obtain the complement of this language that will accept strings that do not end with 0, 1. Next theorem, the regular languages are closed under intersection. Proof: note that L of M1 intersection L of M2 according to De Morgan's theorem is equals to complement of L of M1 union complement of L of M2. Just now we have already proved that the regular languages are closed under complement and union. That is, L of M1 is regular, complement of a language is regular. Similarly, L of M2 is regular, complement of a language is regular. Regular language union regular language is regular and complement of the regular language is regular. Hence, LHS is equals to RHS, and the regular languages are closed under intersection. Figure A is a DFSM L1 which accepts the strings that have 0. Figure B is a DFSM for L2 which accepts the strings that have 1. Figure C is the intersection or the product construction which accepts that have both 0 and 1. So in the figure A, the states are PQ, in B RS, then the intersection DFSM has 4 possible states: PR, PS, QR, QR and QS, where initial state is PR and final state is QS. Next theorem is the regular languages are closed under set difference. L of M1 minus L of M2 is equals to L of M1 intersection complement of L of M2. We have already shown that the regular languages are closed under both complement and intersection. That is, L of M1 is regular, L of M2 is regular, complement of a regular expression is regular, regular expression intersection regular expression is regular. RHS is regular, so LHS must be regular. Hence, the regular languages are closed under set difference. Next theorem is the regular languages are closed under reverse. L raised to R is equals to W belongs to summation star, where W is equals to X raised to R for some X belongs to L. For example, let L is equals to 0, 0, 1, 1, 0, 1, 1, 1. Then L raised to R is 1, 0, 0, 0, 1 and 1, 1, 1. Second, let L be defined by a regular expression 0 or 1 followed by 0 star. Then L raised to R is equals to 0 star followed by 0 or 1. Regular languages are closed under letter substitution. Consider any two alphabets summation 1 and summation 2. Let sub be any function from summation 1 to summation 2 star. Then letter substitution sub is a letter substitution function from L1 to L2 if and only if letter substitution of L1 is equals to string W which belongs to summation 2 star, where for some y belongs to L1 W is equals to y, except that every character C of y has been replaced by sub of C. For example, consider summation 1 is equals to AB and summation 2 is equals to 0, 1. Let sub be any function from summation 1 to summation 2 star. Sub of A is equals to 0, sub of B is equals to 1, 1. Then let sub of A raised to n, B raised to n, where n is greater than or equal to 0 is equals to A is substituted as 0 raised to n, B is substituted as 1, 1, that is 1 raised to 2 n, where n is greater than or equal to 0. Consider one more example. Summation 1 is 0, 1, 2. Summation 2 is AB. Let h be any function from summation 1 to summation 2 star. H of 0 is A, h of 1 is AB, h of 2 is BA. So h of 0, 1, 2, 0 is h of 0 concatenated with h of 1, h of 2 and h of 0. H of 0 is A, H of 1 is AB, H of 2 is BA, H of 0 is A. So the string obtained is AA, BB, AA. H of 0, 1 raised to star 2 is equals to H of 0, H of 1 whole raised to star H of 2. That is equals to H of 0 is A, H of 1 is AB whole star, H of 2 is BA. So H of 0, 1 raised to star 2 is equals to A, AB whole star, BA. In this session, we have seen that every finite language is regular. Some infinite languages are regular. Not all infinite languages regular. The easiest way to prove that a language is regular is to construct a FSM. And the regular languages are closed under union, concatenation, clean star, complement, intersection, difference, reverse and letter substitution. Thank you.